Hey guys, this is Bharani from Edureka, and in this session, we'll be implementing data science concepts with R. I'll start off by giving a brief introduction to data science, and then we'll take a data set and perform data manipulation tasks on it. Following which, we'll find out interesting patterns from the data by visualizing it with the helps of graphs and plots. And finally, we'll build some machine learning algorithms and evaluate their efficiency. So, what is data science? We'll understand that through a story. Now, this is John, and John stumbles upon terms such as data science and machine learning and starts wondering what they exactly are. Now, John decides to go to Uncle George, who is a data scientist, and Uncle George happily helps our curious John. Uncle George tells us that data science is all about making the data talk to us. That is, it is an umbrella term which encompasses multiple domains such as data manipulation, data visualization, machine learning, data reporting, deep learning, and statistical analysis. And for most of his data science tasks, Uncle George uses R, and hence will follow Uncle George's advice and use R for our data science tasks as well. Uncle George tells us some features of R. He tells us that R is Turing complete. That is, whatever computational process it is, it can be done with the help of R. R is also a dynamically typed programming language, which means that the focus is on the value of the object and not on the data type of the object. R also provides more than 10,000 free packages. That is, whatever your need is, there is a package for that. If you want to do data visualization, there is a package for that. If you want to do data manipulation, there is a package for that too. And R can easily be integrated with other popular softwares such as Tableau, SQL Server, and so on. Now it's time to install R on our systems. We can install R from CRAN repository. So let's go ahead and install R. In Google, I'll just simply type out download R. I click on the first link, and since I use a Windows system, I'll be downloading the latest version of R for Windows. The latest version is R 3.4.3. I click on this link and the download starts. Now we would also require an IDE for R. So R-Studio is the IDE. Let's go ahead and download R-Studio. Again, I'll just type out download R-Studio. I'll click on the first link. I select download. Again, since I'm using the Windows version, I'll download the Windows version of R-Studio. So we have both R and R-Studio on our systems, and we've installed it successfully. Now it's time to implement the data science concepts on real life data sets. We'll start off with data manipulation. So you have Uncle George here again. Uncle George tells us that data manipulation deals with simple operations such as summarizing, aggregation, and filtering. Now R provides a specific package for data manipulation which goes by the name of dplyr. And R has some special functions for this purpose, such as select, filter, mutate, and arrange. And for the sake of the case study, we'll be using the H-flights dataset. So let's start data manipulation. We would have to load the dplyr package, and to do that, we'll be using the library function. With the help of the library function, we can load any package. And prior to loading any package, we're supposed to install it. So I click on the install tab, I type out dplyr over here, I select dplyr, and when I click on install, the package will be installed. And since I've already done it, I don't need to install the package again. Since this is done, we would also have to load the H-flights dataset. I load it with the library function. Now it's time to look at the dataset with the help of view function. View of H-flights. H-flights dataset comprises of all of the domestic flights which departed or arrived from the Houston airport. We'll start with the data manipulation task now. The first function is select. With the help of the select function, we can select some specific columns from the dataset. That is, if you would want to select only the first 5 columns from the dataset, we can do that. If our purpose is to select the first 2 columns and the last 2 columns, we can also do that. And otherwise, if you'd want to select only the alternative columns from the dataset, we can also do that. So over here, this is the select function. First, we would have to give the name of the dataset. Since we're working with the H flights dataset, we've given the name of the dataset followed by the names of the columns separated by comma. That is, from the H flights dataset, we are selecting flight number, arrival time, and departure time columns and storing the result into the flight 1 object. Let's have a look at the result. This was the original dataset, and from the original dataset, we've selected only three columns, which are flight number, arrival time, and departure time. Let's look at the second select command. Now, instead of giving the names of the columns, we can directly give the column numbers. That is, from the H flights dataset, we are selecting the fifth, sixth, and the eighth column. So, this is the fifth column, this is the sixth column, and this is the eighth column. So, we selected all of those columns and we've stored those columns into the flight 1 object. So, view of flight 1, again, fifth, sixth, and eighth column from the H flights dataset, and these are the only three columns selected. Now, from the H flights dataset, we are selecting all those columns which have the column name time. That is, if we look at this dataset, then all of those column names which consist of the string time in their column name will be selected. So we see that four columns have been selected: departure time, arrival time, actual elapsed time, and air time. And since all of the column names contain the string time in them, only these columns have been selected. Similarly, in this command, we are selecting all of the columns from year to arrival time. That is, this is the year column and this is the arrival time column. And if I just simply put a colon in between these two columns, I'll get all of the columns between these two. View of flight 1. Now this gives me all of the columns from year to arrival time. Again, instead of giving the column names, we can directly give the column numbers. So from the H flights dataset, we are selecting the first six columns, that is 1, 2, 6. So the result will be the same. View of flight 1. So we've selected the first six columns and stored it into the flight 1 dataset. Now that is done, let's go ahead with the final select command. Now, from the H flights dataset, we are selecting all those columns which start with day and all of those columns which end with time. That is, if we look at this dataset, all of those column names which start with the string day and all of those column names which end with the string time. Let's have a look at the result. Flight 1. So these are the two columns which start with day, and these are the four columns which end with time. Quite interesting, isn't it? So that was the select function with which we were able to select some specific columns from the dataset. Now it's time to head on to the next function, which is mutate. With the help of the mutate function, we can bring in new columns by tweaking the old columns. That is, over here, from the H flights dataset, I am subtracting the air time from the actual elapsed time and storing the result into the actual ground time. So we get a new column which is actual ground time, which is basically air time subtracted from actual elapsed time. Let's look at the flight 1 dataset. This is the actual elapsed time and this is air time. We'll get a new column which is actual ground time. So if you look at these two values, actual elapsed time is 60 and air time is 40. If you say 60 minus 40, you'll get 20, which is actually the actual ground time, which gives you 20. Similarly, we can perform other mutate functions and bring in new columns. In the H flights dataset, we did not have the average speed of the flight. We only had two columns which told us the distance traveled and the air time. Now, since we would also want to see what was the average speed of the flight, we can just obtain it by this formula, which is distance upon air time, and store the result into the new column, which is average speed. So I've stored the result again into the flight 1 object. Let's have a look at the flight 1 object now. This is the flight 1 object. Now we see that a new column has been added, which is average speed, which contains of the average speed of all of the flights. This is done. Now we would want to find out the total time spent in taxi. So the total time spent in taxi is taxi in plus taxi out. View of flight 1. We get a new column which is total taxi. This was taxi in and taxi out. So it was 7 and 13. So that becomes 20 minutes. And hence the total time spent in taxi was 20 minutes for the first row. This would be the final mutate command. In this, we are trying to get a new column which would tell us the total delay for the flight. Initially, we just had delays for the arrival and departure, and we did not have any column which told us the total delay of the flight. And hence, if we would just add the arrival delay and the departure delay, we would get a new column which would tell us the total delay. And we've stored the result into a new column which is time loss. Let's have a look at the flight 1 object. Flight 1, we have a new column which is time loss, which tells us the total delay for the flight. We're done with the mutate command as well. Now it's time to head on to the next function, which is filter. With the help of filter function, we can filter out some specific rows depending on a condition. Like over here, from the H flights dataset, we are selecting only those observations where the distance is greater than 3000 miles. So let's have a look at the flight 1 object. Let's look at the distance column. This is the distance column. We see that all of the values are greater than 3000. Just to be sure, we'll also find out the range for this. Range of flight 1 dollar distance. Now we see that the minimum value of distance is 3266 and the maximum value of distance is 3904. And hence this all of the distance values are about 3000. We'll head on with the next filter command. Now from the H flights dataset, we are selecting only those unique carriers which have the tags OO, US or AA. Let's look at the result. View of flight 1. We'll look at the unique carriers. We can use a table function to find out what are the unique carriers present. So table of flight 1 dollar unique carrier, which tells us that there are only 3 unique carriers, which are AA, OO and US. And hence, out of these 23,387 entries, only 3 unique carriers are present. Time for next filter command. Now this is quite interesting. Over here, from the H flights dataset, we're trying to understand, are there any values where the total time spent in taxi is greater than the total time spent in a plane? That is, taxi in plus taxi out is greater than air time. View of flight 1. We have taxi in and taxi out over here. We have the air time over here. And if we look at the second row, we see that taxi in plus taxi out is 50. And over here, the air time is 43. That is, the person has spent 43 minutes in the plane and 50 minutes in the taxi. Similarly, if we look at the third row, 35 plus 10 is 45. And again, the time spent in plane is 43 while the time spent in taxi is 45. Thus, all of these 1389 entries consist of those observations where the person has spent more time in a taxi than the plane. You can also give multiple conditions in the filter command. So over here we are trying to see how many of the flights have departed before 5 a.m. and how many of the flights have arrived after 10 p.m. That is, departure time is less than 500 and arrival time is greater than 2200. View of flight 1. This is the departure time and this is the arrival time. We see that all of these entries, the arrival time is greater than 2200. That is, the flights have arrived after 10 p.m. This would be the final filter command. And over here, from the H flights dataset, we are trying to see how many of the flights were destined towards JFK airport, and out of all of those flights, how many of them were cancelled. That is, since we use AND over here, both of these conditions need to be satisfied. C needs to be capital over here. Let's make it capital. This is done. View of flight 1. Let's look at the destination column. We see that there are 18 entries, and for all of those 18 entries, the destination is JFK. And again, for cancelled, we see that for all of the 18 entries, the value for cancelled is 1. Now, you might also see that there are a lot of NA values over here, and that is because Since the flight was cancelled, there is no departure time or arrival time for all of these flights. That was filter. Then comes the arrange function from the deployer package. With the help of arrange function, we can either order the data set in ascending or descending order with respect to one particular column. So we are ordering the H flights data set with respect to the departure delay column. Let's look at the result. Flight 1. Let's look at departure delay. We see that this column has been arranged in ascending order. So the minimum value is minus 33, and obviously the maximum value would be the last row of this data set. This arrange function is quite interesting. So we are adding the departure delay plus arrival delay. That is, we'll be arranging the data set in such a way where the total delay is minimum will be coming at the top, and where the total delay is maximum will be coming at the bottom. View of flight 1. Let's look at departure delay and arrival delay. So these are two values. We see that arrival delay, the minimum arrival delay is minus 70 and the minimum departure delay is minus 1 over here. So when we add these two, the total arrival delay plus departure delay becomes minus 71. So since this is the minimum value, this comes at the top. We're done with arrange. Now it's time for the next function, which is summarize. Now, summarize is a very handy function because it gives us quick results. Now, we're trying to find out from the H flights dataset what was the minimum distance traveled and what was the maximum distance traveled. All we need to do is select the dataset and give the functions which would give us the summarized result. So, minimum of distance and maximum of distance. We see that minimum distance traveled by any flight is 79 miles and the maximum distance traveled by any flight is 3,904 miles. We'll head on with the next summarize function. In this, from the H flights dataset, we're trying to determine what was the minimum arrival delay, the average delay, and the maximum arrival delay and the standard deviation in arrival delay. So this is the earliest, average, latest, and SD. So this tells us on an average there was an arrival delay of 7 minutes and the maximum arrival delay was 978 minutes. Interesting observations again. This is done. Now with the help of the pipe operator, we can combine the different functions from the deployer package. The pipe operator comes from the migrator package and it helps us to connect objects. So what we're doing here is from the H flights dataset, we are selecting only those columns which contain the string time, and from those columns we are filtering out rows where airtime is greater than 60. Let's look at the result. View of flight 1. So from the H flights dataset, we've selected only those columns which contain the string time, and that is why we have departure time, arrival time, actual elapsed time, and air time. And for all of these observations, the air time is greater than 60. Again, just to be sure, let's find out the range of this. Range of flight 1, air time. So we see that the minimum air time was 61 and the maximum air time was 41. And hence the condition is satisfied over here. Let's combine new functions and new conditions. Over here, from the H flights dataset, we are filtering out those observations where unique carrier is WN. From all those observations, we are summarizing the result and we're trying to find out the minimum air time for that result. So what we see is, out of all the observations where unique carrier is WN, the minimum air time is 25 minutes. That was data manipulation with the help of deployer package. Let's head on to the PPT again. So we're done with data manipulation. Now it's time for data visualization. And Uncle George is back. Uncle George tells us that data visualization deals with understanding the significance of data through graphs and plots. And for the sake of the case study, we'll be using the house dataset. Now let's visualize the house dataset. This is the dataset, guys. It comprises of columns such as price of house, the lot size, whether the house has a waterfront or not, what is the land value, whether the house is newly constructed or not, and other columns, so on. For the visualization purpose, we'll be using the ggplot2 package. So let's load it. Again, we can load any package with the help of the library function. Prior to loading any package, we're supposed to install it. So I click on the install tab, I type out ggplot2 over here, and when I click on install, the package will be automatically installed. This is done. Now it's time to do univariate analysis with the help of a histogram. Now, with the help of ggplot2, we can add multiple layers over a single layer. That is, what we are doing over here is, we select the data set first, that is, we obtain the data layer, and onto the data layer, we assign new aesthetics. So, we've selected the house data set, and from the house data set, we map the price data column onto the X aesthetic. So, this is the house data set, and we've mapped the price data column onto the X aesthetic. So we're done with the data layer, we're done with the aesthetics layer. Next comes the geometry layer. And with the help of geometries, we can select any plotting technique. That is, it can be either a scatter plot, box plot, histogram, a bar plot, and so on. Since over here we are plotting a histogram, we're doing univariate analysis. That is, we're trying to understand the distribution of price. We see that the average price is around 2 lakhs. You see these values 2e plus 0.5, 4e plus 0.5, 6e plus 0.5. They basically mean 2 into 10 power 5 and 4 into 10 power 5, which would basically amount to 2 lakhs, 4 lakhs, and 6 lakhs. That is, the average price of the house is somewhere around 2 lakhs, and the maximum price of the house is somewhere closer to 8 lakh. Now let's add color to this plot. Until here, the command is the same. So we're adding new attributes into the geom histogram function, which are fill and call. So I'm assigning the value pale green 4 to the fill attribute, and I'm assigning the value green to the call attribute. You see this color, this is pale green 4, and you see the color for the boundary, that is green. So this was univariate analysis with the help of a histogram. Now it's very important to understand where to use a histogram and where to use a bar plot. So whenever you would want to see the distribution of a continuous variable, you'll go with a histogram, and wherever you'd want to see the distribution of a categorical variable, you'll go with a bar plot. Since we've already seen the distribution of a continuous variable, which was price, now it's time to see the distribution of a categorical variable, which is air conditioning variable. So I've selected the house dataset, and from the house dataset, I'm mapping the air conditioning column onto the X aesthetic, and the geometry selected by me is bar plot, and the color is orange. So let's zoom this and see. We see that most of the houses do not have centralized air conditioning. That is, this distribution is larger than this distribution. So the simple inference is most of the houses do not have air conditioning, while very few houses have centralized air conditioning. This was histogram and bar plot. Next comes a scatter plot. Again, we've selected the house dataset. Now, a scatter plot is used for multivariate analysis. That is, to observe how does one variable change with respect to another variable. And we've mapped the price data column onto the Y aesthetic, and we've mapped the living area data column onto the X aesthetic. The color is determined by the number of rooms, and the geometry used is geom point, which will give us a scatter plot. So we've mapped price onto the y-axis, living area onto the x-axis, and the color is determined by the number of rooms. Let's zoom this. We see that there is a linear relationship between the price of the house and the living area. That is, as the size of the living area increases, the price of the house also increases. Now, if you look at this part, that is the colors, if you look at these colors, which is mostly green, we see that green color determines that the house has either 4 or 5 rooms. And if the house has either 4 or 5 rooms, then we can conclude that its living area is low, and also the price of the house is also low. And you see these dots over here, the color is pink. So we can say that if the color is pink, then the house would have around 12 rooms. And if the house has 12 rooms, then obviously the size of the living area would be large, and also the price of the house would also be high. So these are the sort of inferences which you can make with a scatter plot. This is done. Next, we'll be making a box plot. A box plot is used to understand how does a continuous variable change with respect to a categorical variable. And again over here, we selected the house data set, and on the house data set, we've mapped the price onto the Y aesthetic, and we've mapped the number of rooms onto the X aesthetic. The color is determined by the number of rooms, and the geometry is box plot. So we see that as the number of rooms increases, the price of the house increases. You see these lines, these are the median values. Again, so the same inference, as the number of rooms increases, the median value of the price of the house also increases. So that was box plot. So these were the commands with which we did a bit of data visualization with the help of the ggplot2 package. Let's again head on to the PPT. We're done with data manipulation, we're done with data visualization. Now it's time for machine learning. Uncle George is back again. Now Uncle George tells us that machine learning is the field that deals with how to make the computers learn. These are the different types of machine learning algorithms which are generally present. So broadly speaking, we have supervised learning, reinforcement learning, and unsupervised learning. In supervised learning, it is a type of machine learning algorithm that uses a known dataset to make predictions. That is, we already have a set of labels, and from those set of labels, we build a model and we predict these values on a new dataset. So let's go ahead and do it practically. We'll start with linear regression. Linear regression comes under the purview of supervised learning, and since it comes under the purview of supervised learning, it has labels, and we try to determine how does one value change with respect to another variable, or in simpler terms, we try to understand how does the dependent variable change with respect to the independent variables. Since we'll be building the linear regression algorithm on top of the empty cast dataset, let's have a look at this. So this is the empty cast dataset, and we try to determine how does the miles per gallon column vary with respect to other columns. Now for any machine learning algorithm, we're supposed to split the data into two parts, which is training and testing. And to do that, we'll be needing the CA-tools package, which gives us the sample.split function. With the help of the sample.split function, we can split the observations into two categories. One category of the observations will have labels marked as true, another category of observations will have labels marked as false. So over here, since we're trying to predict the values of the miles per gallon, we've taken this as the first parameter, and the split ratio is 0.65. That is, 65% of the observations will have the true label and 35% of the observations will have the false label. The splitting is done. Now it's time to divide the data. So all those observations where the split label is true, we'll select all those observations from the empty cast dataset and assign them to the training set. Again, similarly, we'll select all of those observations where the split tag is false and store them in the test set. Let's look at the number of rows in train and test set. N row of train tells us that there are 20 rows in the training set. Similarly, n row of test tells us that there are 12 rows in the test set. Since the division is done, now it's time to build the linear model on top of the training set. So you see the tilde symbol over here? The value which is given on the left side of the tilde symbol is the dependent variable, and the value which is given on the right side of the tilde symbol are all the independent variables. And since we've given a dot over here, that basically means that we're trying to determine how does miles per gallon vary with respect to all other columns of the dataset. That is, miles per gallon is the dependent dataset and all other columns are the independent variables. We build the model and we've stored the result in mod 1. This is done. Now it's time to predict the values. So we select the mod 1 and we evaluate the results on top of the test set, and we store the result in an object which goes by the name of result. Let's look at this view of, so these are the predicted values. Let's combine the actual values and the predicted values and store the result in a new data set. So actual values, which are the miles per gallon values from the test set, and the predicted values which are stored in the result set. I'm combining these two values and I'm storing them in a new data set which is named final. View of final will give us this. So we see that these are the actual values and these are the predicted values. Now it's time to find out the error in prediction. Now before we do that, since it is a matrix, we're supposed to convert it into a data frame. So as.dataFrame, with the help of this function, we can convert a matrix to a data frame. We've converted the final, which was initially matrix, into a data frame. Since that is done, It's time to find out the error in prediction. Finding out the error in prediction is quite simple. We just need to subtract the predicted values from the actual values. That is, actual minus predicted gives the error in prediction. That is what you see over here. Final dollar actual minus final dollar predicted is the error. View of final. So these are the actual values, these are the predicted values, and this is the error in prediction. Now, to evaluate the performance of any model, we have something known as root mean square error. So the lower the root mean square error, the better the model. So root mean square error is again simple. So we need to square the error, find out its mean, and then followed by the square root. Store the result in RMSE1. Let's look at RMSE1. So RMSE1 is 52,608. Now to compare this model with another model, let's build a new one. Now in this LM function, in the independent variable side, I am selecting all of the variables except the number of gears and the number of carburetors. That is all of the columns except these two columns. And again, the dependent variable is miles per gallon. Data is the training set, and I'm storing the result in mod 2. Now that this is done, it's time to predict the values on the test set. So this is the mod 2, which is the built model, and I'm trying to predict the values on the test set, and I've stored the result in the result object. It's time to bind the actual values and the predicted values. So the actual values which were in the test set and the predicted values which are stored in result, I'm combining those two and storing in the final object. This is done. Let's look at final. So these are the actual values and these are the predicted values. Again, we would need to find out the error in prediction. Before we do that, let's convert this matrix into a data frame. Again, we'll be using the as.dataframe function to convert the matrix into a data frame. We'll use the cbind function now to combine this final data set with the new column, which is error. Error we'll find out by subtracting predicted values from the actual values. View of final. So these are the actual values, predicted values, and this is the error in prediction. Now it's time to find out the root mean square error. So we'll find out the square, then we'll get the mean, and finally we'll perform the square root and store it in RMSE2. Let's see what is the value of RMSE2. We see that the values of RMSE1 and RMSE2 are same. Both of them give the value of 52,608. That is, we cannot say which model is better than the other model, and hence both of the models are similar in terms of accuracy. That was linear regression, which comes under supervised learning. So we're done with linear regression, and we've used the empty cast dataset to perform linear regression. Now it's time to perform classification. Again, classification comes under the purview of supervised learning, and since it comes under supervised learning, classification also has labels. So if you look at this slide, we see that we have an observation and we're trying to assign a label to this observation. And if we assign the label of boy to this observation, the classification will be right. And if we assign the label girl to this observation, the classification would be wrong. For the sake of the case study, we'll be working with the census data set. So let's go ahead and do that. View of census data. This is the census data set, which comprises of columns such as age of the person, his working sector, race, his sex, the native country, and his salary. And here we're trying to classify the salary, that is, whether the person earns greater than 50k or less than 50k. This is the classification that we are trying to do over here. Let's go ahead and do that. We've already looked at the data set. Now it's time to perform classification, and we'll be building a decision tree to do this. R provides us a package called rpart, which stands for recursive partitioning, and recursive partitioning can be used to perform a decision tree algorithm. Again, prior to building any machine learning algorithm, we're supposed to split the data into training and testing. That is why, again, we're supposed to load the CA tools package. Once that is done, we'll use the sample.split function, and since we would want to classify the salary column, we'll give this as the first parameter, and the second parameter is the split ratio. That is, 65% of the observations will have the true label and 35% of the observations will have the false label. And I'm storing the result in my split object. Now, out of all of those observations where the label is true, they have been selected and stored in the training set. Similarly, All of those observations which have the label false have been selected and stored in the test set. So the splitting is done. Now it's time to build the decision tree algorithm on top of the training set. We'll use the R part function to build the decision tree algorithm. Salary will be the dependent variable and all of the columns will be the independent variables. And that is why we've given salary on the left side of the tilde symbol and dot has been given on the right side of the tilde symbol. That basically means all of the variables except the salary column will be the independent variables. The data is trained and method used is class because this is a classification algorithm and we're trying to determine whether the class is less than 50k or greater than 50k. We'll store the result in mod classify. Once the model has been built, we would want to predict the values on the test set. So we've selected the model and we are predicting the values on the test set. And again, since this is a classification algorithm, the type given is class. And the result is stored in the result object. So view of result. These are the predicted values. Let's determine the accuracy of this prediction. We'll be loading the caret package and E1071 package for this purpose. The caret package consists of the confusion matrix function which helps us to determine the accuracy of the prediction. So let's go ahead and determine the accuracy of the prediction. So this is the confusion matrix and this is a table which tells us that these were the actual values and these were the predicted values. Now wherever in the actual values, if the value was less than or 50k and the prediction was also less than or 50k, these are all those values. And over here, these are the values where the actual was greater than 50k, but it was predicted that these values are less than or equal to 50k. That is, this has been predicted correctly, but this has been predicted wrongly. Again, over here, actual is less than or equal to 50k and predicted is greater than 50k. So this is wrongly classified. And this, we see that it is greater than 50k and greater than 50k. So this is correct classification. So if you look at the left diagonal, this stands for those values which have been correctly classified. Now to find out the accuracy, we'll just add 7992 plus of 1469, which consists of all those observations which have been correctly classified upon all of the observations, that is 7992 plus of 660 plus of 1275 plus of 1469. So this is the accuracy of the model. Again, if you compare this with this, it is the same. So this tells us that the accuracy is 83%, and again, as calculated by us, the accuracy is 83%. That is, 83% of the values have been correctly classified, while the other 17% of the values have been wrongly classified. That was classification, which was under supervised learning. Now it's time to learn unsupervised learning. In unsupervised learning, the observations do not have any predefined labels. So if we look at this slide, these are a group of observations and these have been grouped into two clusters. And that has been done on the basis of similar features. That is, there is high intra-cluster similarity for all of these observations, and again, there is high intra-cluster similarity for all of these observations. But when we talk about inter-cluster similarity, that is, if we talk about the first cluster and the second cluster, there is very low similarity. This is the idea behind clustering. There is high intra-cluster similarity and low inter-cluster similarity. For the case study, we'll be working with the iris dataset. Let's go ahead and cluster these observations. This is the iris dataset, which comprises of 5 columns: sepal length, sepal width, petal width, and the species column. Let's look at the different species of the iris flower. Table of iris $species. We see that there are 3 species of the iris flower, which are setosa, versicolor, and virginica, and all of these 3 species are equally distributed. Now we'll be building a k-means algorithm for the clustering purpose, and the k-means algorithm only works with continuous variables, and hence we're supposed to remove the last column, which is a categorical variable. So we'll remove the last column and store it in a new dataset, and we'll name it as iris4. Let's have a look at the iris4 dataset. This is the new dataset which comprises of only 4 columns. Now let's build the k-means algorithm. For the k-means function, we give the dataset and we give the number of clusters. And we store the result in k1. Let's bind the result to the iris4 dataset again. View of iris4. So these are the 4 columns and these are the clusters. Let us use the table function and let us see how has the clustering been done. Table of iris4 $k1 cluster. You see that there are 62 observations in first cluster, 38 observations in second cluster, and 50 observations in third cluster. Now let's also combine the species data column to this and let's see the result. View of iris4. So we have the k1 cluster and also the species column. Let's go down and let's analyze this properly. We see that for the first 50 observations, the cluster number is 3. That is, all of the first 50 observations belong to the third cluster and all of these observations belong to the species Setosa. So what we can conclude from this is all of the species of Setosa family have been clustered into the cluster 3. Again, if we look at this, we have Virginica and versicolor. Now this seems to be quite ambiguous. We cannot conclude anything. So we see that out of Virginica and versicolor, some of the observations have been clustered into the cluster 3 and some of the observations from versicolor and Virginica have been grouped into cluster 2. So this was clustering, which comes under the purview of unsupervised learning. So this is the end of the session. Summing up, we've learned data manipulation. We've worked with the dplyr package which provided us functions such as select, filter, mutate, arrange and summarize. After which we've visualized the data with the help of the ggplot2 package. Then we've understood some machine learning algorithms. We've understood supervised learning and unsupervised learning. We've learned that supervised learning consists of labels and unsupervised learning does not consist of labels. And in supervised learning, we've implemented linear regression followed by classification. And for unsupervised learning, we've built the k-means clustering algorithm. So thank you for watching the video. Hope you enjoyed it.
I hope you enjoyed listening to this video. Please be kind enough to like it and you can comment any of your doubts and queries and we will reply to them at the earliest. Do look out for more videos in our playlist and subscribe to our Edureka channel to learn more. Happy learning!